Let's look at the graphs of secant and cosecant. First, looking at the graph of secant, remember that the reciprocal identity tells us that secant is equal to 1 over cosine. Therefore, when cosine is 0, secant will be undefined or will lead to vertical asymptotes at those zeros of cosine. So if you notice here in the graph, we have the cosine graph here in orange, and at the zeros of the cosine graph, we end up having vertical asymptotes for our secant graph. The same is true for cosecant and sine. So notice on our sine graph here, when I have the zeros of our sine graph, then we would have vertical asymptotes at those pieces as well. Since sine is an odd function, cosecant will also be an odd function. And since cosine is an even function, secant is also an even function. Personally, when I choose to graph secant and cosecant, I graph it like I'm graphing sine and cosine very gently. Find the zeros of that, make my vertical asymptotes, and then just do the 1 over components of that. So there is some like graphing steps if you want to look at those, but I just want to show you an example of each one. So cosecant is 1 over sine. So if I had -3 sine of 4x, I know that my period would be pi over 2, and I have a negative stretch. So what would normally go from 0 to 2 pi is going to go from 0 to pi over 2, which means halfway would be pi over 4. And instead of having my sine curve go this way, I have a -3. So my sine curve is going to go like so. And then you can keep going if you want to for multiple pieces. All right, let me change my color for my now cosecant graph. All right, so therefore for cosecant, I'm going to have vertical asymptotes everywhere where my sine function is 0. And then that 1 over piece actually just means that you're going to have like a reciprocal type identity for your cosecant. So it's going to end up looking something like this. So that purple graph without the blue graph would be your cosecant graph. All right, let's go ahead and graph a secant function. So I'm going to do the same thing where I say, okay, secant of theta is 1 over cosine theta. And so if this was y equals 4 cosine of pi over 3x minus pi over 2 plus 1, then I would know that I have a stretch of 4. I have a period of 2 pi over 3 multiplied by the reciprocal period of 6. And when I do my shift here, if I factor out a pi over 3, I get x minus pi over 2 over pi over 3, which ends up giving me pi over 3 on the outside and then x minus 3 halves on the inside plus 1. So let's go ahead and graph that cosine graph first. So normally cosine would go here, 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 and here over a period of 2 pi, but my period is 6. So then this point is 3. But then I also have to move this over by 1.5. Well, that's kind of nice actually, because 1.5 would be where these are, and then 4.5. So I'm just going to move everything over by 1.5. I'm then going to stretch by 4 and then move everything up 1. So I'm going to just do that on like, let's do a different graph. So we could stretch these by 4 and then move them all up 1. And I know I don't have like a scale on here or anything like that. All right, so here's my cosine graph. Under those transformations. And I could keep going if I wanted to. So at 6, I'd be like here. Okay, so here's where it's going to be a little bit tricky, because I need wherever I have my zeros, right? That's going to be my vertical asymptotes of my secant graph. And then I can just draw in that reciprocal relationship that got kind of muddled right there. And then erase your cosine graph. And that's how we do these reciprocal graphs for secant and cosecant.